Hi, I'm Jeremy, one of the authors of Machine Learning Refined, a university textbook about machine learning foundations, algorithms, and applications. Today I'm going to show you a little bit of code you can play with. You can download this code from our website, which I'm showing you here, at mlrefined.com. You can also find a variety of sample chapters from the book on this website, as well as video tutorials on a range of machine learning topics. The code I'm going to show you today illustrates the algorithm called Newton's method, which is one of the most popular numerical optimization schemes used in practice in machine learning today. This is described in much detail in Chapter 2 of the textbook, which I'm showing you here. You can download this chapter for free from the book website. The next batch of demos I'm going to show you illustrate Newton's method, which is described in detail in section 2.2.4 of the text. These are essentially an interactive version of figure 2.11 here, where we show how Newton's method works when it's applied to a convex function, g of w, and a generic non-convex function, g of w here. So, first, when applied to a convex function, if we initialize Newton's method at w0 here, we take a quadratic approximation to that point, given by the second order Taylor series approximation. Now that's going to be an upward facing cup, or quadratic, because the function is convex. We travel to the minimum of that quadratic, given by the little red x here, hop back onto the function, and that value down on the horizontal axis is our first step. We then repeat. We take a quadratic approximation to g at w1, travel to its minimum, given by the little red x there, hop back onto the function, that gives us w2. And then we repeat. Make another quadratic approximation, travel to the minimum of that, etc. Again, all of these quadratics will be facing upward, okay, because the function is convex. And generally, when applied to a convex function, Newton's method will always hop downhill and reach a minimum of the function. Now, when applying Newton's method to non-convex functions right out of the box, it's important to be aware of potential problems that can arise with the algorithm when it travels through or is initialized at concave portions of a function like that. So this is illustrated figuratively in the bottom panel here. If we initialize at w0, where g is convex or facing upward, then the method tends to work similarly to the case when g itself is convex. That is, we initialize it at w0. The quadratic approximation is a quadratic facing upwards. We travel to its minimum, given by that red x. We hop back onto the function, that gives us the first step, w1. We then repeat. We make another quadratic approximation, now at w1, travel to its minimum, and that gives us the second step. This will tend to give us decreasing values in g, and we'll end up at a minimum around here. Now, if you initialize at a w0 that is on a concave portion of the function g, like the one illustrated here, Newton's method will not travel downwards towards a minimum. It will actually travel upwards towards a maximum of the function. Now, why is that? Because when you initialize at a w0 that is on a concave portion of g, the quadratic approximation at that point is also concave or facing downwards. That means when you're looking to travel to the stationary point of that quadratic approximation, it's no longer a minimum, it's a maximum, like the one illustrated here. So here's the first concave quadratic approximation to g at this w0. There is the stationary point, which is a maximum. Then we hop back onto the function, so we're traveling upwards, not downwards. This is just something to be aware of when you use Newton's method right out of the box to minimize non-convex functions, and will also be illustrated in the demo. Okay, let's look at some code. I'm going to show you two demos now that essentially reproduce this figure. The first one reproduces Newton's method as shown here applied to a convex function. The second one reproduces the bottom panel here that shows Newton's method applied to a generic non-convex function. Both of the demos I'll show you right now are written in Python, but you can find equivalent ones written in MATLAB on the book website as well. So let's look at them. The first one is called convex newt surrogate. When I press run here, up will pop the picture of a generic convex function. Now anywhere I click in this window, I'm going to initialize a run of Newton's method. So if I click here, I'm initializing Newton's method at this w0. And here's the first quadratic approximation. There's the minimum of that quadratic in black. I travel to that and hop back onto the function. Do that again. There's the second quadratic approximation. It's minimum in black. I travel there and hop back onto the function, and then I repeat. Now you're only going to need about 3 to 5 iterations of Newton's method to minimize this function. The final point will be shown in red here. Of course, we've slowed down Newton's method so you can see each quadratic approximation, okay, at each step. In practice, Newton's method is much faster than this. The second piece of code I'm going to show you is called non-convex Newt surrogate, and it illustrates how Newton's method generally behaves when applied to non-convex functions, like that lower panel in figure 2.11. So when I press run here, I'm just going to pop a picture of a generic non-convex function. Make it a little bigger. This demo works very similarly to that convex demo. So anywhere I click here, I'm going to initialize a run of Newton's method. So if I click here on a convex portion of the function, I initialize here. I have now a convex quadratic approximation of the function. I travel to its minimum, hop back onto the function, and repeat. So if I start at a good point on a convex portion of this function, I'm going to tend to end up at a local minimum. Likewise, let's run it again. Here's a fresh version of that non-convex function. Likewise, if I start at a concave portion of the function, I'm going to tend to climb to a local maximum. So if we start here, notice each of those quadratic approximations are now concave. So I climb to a maximum. There's the quadratic approximation. It's maximum in black. Hop back onto the function and repeat. As with that convex demo, the point of convergence here is shown in red on the function. Using this demo, we can also show you another potential issue with applying Newton's method right out of the box to minimizing a non-convex function that we couldn't show you very easily in the bottom panel of 2.11 because it's difficult to show using a static image. This problem is essentially that with Newton's method applied to a non-convex function, you can pretty easily hop around from convex to concave regions of the function depending on your initialization. Okay? Let's illustrate. So we'll press play again, pull up another version of that non-convex function. Now, if I initialize Newton's method around here, right, I want it to go downhill and reach this minimum here. But notice if I initialize, the quadratic approximation is going to be huge, and its minimum is going to lead me, when I hop back onto the function, to a concave portion of g. Now I'm going to start climbing towards a maximum. Right? I don't want to do that, but that's just the nature of Newton's method when you apply it right out of the box to minimizing a non-convex function. Again, I started at this convex portion of the function. Right? I initialize at w0 here, but that quadratic approximation was so wide that its minimum led me, when I hop back onto g, to a concave portion of the function, and then I climbed until I reached the maximum here shown in red. So this is just another potential issue with Newton's method when you apply it to a non-convex function right out of the box that you can see pretty easily by playing around with this toy demo.